So now we have discussed about representing positive integers in our system, which is actually very easy. So let us now discuss how to represent negative integers in our system using zeros and ones. So what's the problem? What we want to do is that given a negative integer, we want to assign a binary representation to it in terms of just zeros and ones. So consider a negative integer s. Assume that its binary form is xn to x1, where this is the least significant bit and xn is the most significant bit, and henceforth we'll actually start counting from 1, not from 0. So now we can also, given this number over here which we are representing, we can also expand it to represent an unsigned. Unsigned means without a sign, assumed to be positive, number n. So we can interpret this binary sequence here in two ways. One is we can interpret it as an unsigned number, so we'll get n, or we can represent it as a number with a sign and we'll get s. So what we need to do is we need to create a mapping from the set of all the numbers with a sign, which can include both positive numbers as well as negative numbers, to a set of binary unsigned numbers called n. So this mapping would essentially tell us how to represent a number, be it positive or negative, using a set of binary bits. So let the set of positive and negative numbers be called S, and let each number, irrespective of its sign, positive or negative, be mapped to a sequence of binary numbers, and we can alternatively interpret this number as a positive number, and let's call this set as n. If we find a mapping, we'll be able to represent both positive as well as negative numbers using a binary representation. For the positive numbers, we already have some idea from our previous discussion, but our previous discussion does not cover negative numbers, so this needs to be covered over here. So let's now take a look at properties of the mapping function. So preferably you need a one-to-one mapping, which means that given a certain sign number, it needs to have only one binary representation. So also the thing is that all the entries in the set S that we need to map should be mapped. It should be easy to perform arithmetic operations on them, such as addition and subtraction. And so these are our three main assumptions. So let's look at one of the simplest possible ways of doing it. So you assume an n-bit number system, a number system in which we have n bits. So n bits basically means that in our number system we will represent every number by a sequence of n bits, right? N binary bits, where they can be from xn to x1. Every number will be mapped with n bits. So we also want to introduce this function sign bit u, which if u is less than 0, if the number is less than 0, this sign bit will return 1. If u is greater than or equal to 0, it will return 0. So essentially the number is positive or 0, the sign bit is 0. If the number is negative, the sign bit is 1. So this is a function that we want to introduce. So let's first look at a very simple kind of representation called a sign magnitude base representation. So here what we do is that the way we define the mapping is something like this, that we define a function fu where u is, where u can be a negative number or a positive number. So we consider the sign bit, multiply it with 2 to the power n minus 1 and add it with the absolute value of u, or alternatively we can think that the absolute value of u is the least significant portion of the representation, and the sign bit, which is negative, which is 1 if the number is negative, is the MSB of the representation. So this number system is actually very simple. So let's look at an example. So let's consider minus 5. So minus 5, we first take the binary representation of plus 5, which is 101, and its sign bit is equal to 1 because the number is negative. So this is the representation that we have. If we consider plus 5, that's also very easy. We take 101 and we treat the most significant bit as 0. So one thing that we can immediately see over here is that this number that we have in this representation, a positive number is being represented in exactly the same way as we had discussed. For a negative number, we just add a 1 before it. Consider one more example, minus 3. So we first write the representations of plus 3 and then we add a 1 as the MSB digit because the number is negative. So what are the problems? There are two representations for 0. So 0 can, both of these are valid representations because the rest of the bits are all 0 and the sign bit is either 0 or 1 where, it does not matter. But still there is a problem in the sense that you're having a positive 0 and a negative 0. So addition and subtraction are difficult. We can clearly see if we just regularly add them as binary numbers, then there is a problem. So the most important takeaway point is, yes, we introduced a sign bit. The sign bit did have some advantages, no doubt. However, it introduced more problems than it could solve. For example, there are two representations of 0, which is something that we don't want. So now let's look at the ones complement representation, which is very simple. Let's first look at the examples. So if you have plus 3, it gets represented in the same way as other positive numbers as 0, 0, 1, 1. If we consider minus 3, what we do is that we just invert every single bit of 0011 to get 1100. Similarly, if we consider plus 5, we take the regular unsigned representation of plus 5, which is 0101, and if we consider minus 5, then what we basically do is that we invert every single bit of plus 5 to get minus 5. Here also you will notice that the notion of the sign bit has also come in the sense that for numbers that are positive, the MSB, the most significant bit, is 0, and for numbers that are negative, the most significant bit is 1. So in a sense, the notion of the sign bit has also come, that positive numbers will start with a 0 and negative numbers will start with a 1, which helps us distinguish between positive and negative, but it does not confer any more mathematical properties. So let's look at the problems of this representation. The problems of this representation are like this, that there are two representations for 0, which is something that we wanted to avoid. So 0, 0, 0 is also 0 and 1, 1, 1 is also 0. And this is not in our best interest in the sense we didn't want it. It introduces ambiguity into the number system. It is easy to add positive numbers. How do you add positive numbers? Let's give a simple example. Let's assume a number of the form 3, 0, 0, 1, 1, and you want to add this 3 plus 2. Well, you can do simple binary addition as you do decimal addition. So you add 1 and 0, you get 1. You get 1 and 1. So 1 plus 1 is 2. So 2 in binary is 1, 0. So you write 0 here. You have 1 as the carry. So you again write 1 over here. So this is 0, 1, 0, 1, which is 5. This is absolutely fine. It's easy to add positive numbers. Unfortunately, it's hard to add negative numbers in this particular representation and that is the sad part of doing this, that adding negative numbers, so negative numbers cannot really be added the way that we added positive numbers, and that will create some problems for us, which is not something that we wanted. So if you want to see, so let's consider an example. So let's say we want to add 3 plus minus 2. So which is 3 minus 2? The answer should be 1. So 3 is 0, 0, 1, 1. Minus 2 is, well, let's consider plus 2. This is plus 2, so we invert every bit of it, 1, 1, 0, 1. Then let's add them. So 1 plus 1 is 0, and the carry is 1, because 1 plus 1 is 2. So the carry is 1. 1 plus 1 is again 0, 1. 1 plus 1 again 0, 1, again 0. So clearly this answer is not correct, this answer is wrong, and this produces an output carry of 1, which is again, not correct. So the answer should have been equal to 1 over here, which is clearly not the case. So we do not have a number system where it's easy to perform arithmetic operations on both positive and negative numbers. So, but nevertheless, the point to note is the idea of a complement, that we can take the complement of every bit and try to represent that as a number. So there can be some merits to it, but well, so we have seen two ideas, the idea of a sign bit and a complement. Individually, these ideas are not that strong. So before we move forward, let me explain this formula that I have skipped. So here, what are we trying to do? We are considering a number u which can either be positive or negative. We are trying to map it. So this is a set S. We are trying to map it to a sequence of binary numbers, uh, a sequence of binary digits where n is its unsigned or positive form. So for positive numbers, we do nothing. It is u itself, where u is greater than or equal to 0. And for negative numbers, what we do is we take the value of u and we complement every single bit of it, where the tilde sign is also the sign for a bitwise complement. Alternatively, what we can do is that, so you consider minus 3. How did we get here? We took 0, 0, 1, 1, and we essentially subtracted this number from this number. So if you subtract anything from 1, you actually get its complement. We can clearly see why. 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, which is, lo and behold, the representation for minus 3. These methods are algebraically equivalent. So let's say given a Boolean variable x, if I consider x complement, that is also the same as 1 minus x. Why is this the case? Assume that x is 0. X complement is 1 and 1 minus x is also 1. Assume x is 1, x complement is 0 and 1 minus 1 is also 0. So what we are doing over here is that, so 2 to the power n minus 1 in a 4-bit number system would be 15, which is represented as all ones. So to take a complement of a number, we can also subtract its absolute value from 2 to the power n minus 1. So we'll get the complement of the number. So there are two ways of thinking about how to take a ones complement. One is we take a complement of every single bit, or we subtract the number from 2 to the power n minus 1. In this case, n is 4 because we have 4 bits. So 2 to the power n minus 1 is 15. So we can subtract it from 15. In a sense, it's equivalent to complementing every single bit. So as we discussed, this approach has its set of problems. The biggest problem is there are two representations for 0, and adding a positive to a negative number or a negative to a negative number is hard, and this is not something that we would want to do. So then let's consider one more approach called a bias based approach, which is used in a different number system. We'll have a chance to talk about it. So you consider a 4-bit number system with a bias equal to 7. So what are we trying to do? We are saying that you take any number, its representation is a number plus the bias. Fine. So let's see minus 3. Its representation would be minus 3 plus 7. So minus 3 plus 7 is equal to 4, and its binary representation is 0, 1, 0, 0. Similarly, if you take plus 3, it will be 3 plus 7, which is equal to 10. And this is exactly what we have, 8 plus 0 plus 2 plus 0, which is 10 in decimal. If you want to add two numbers, it's easy. So in this case, addition of numbers is easy. All that we need to do is the representation of u plus v, f of u plus v, is fu plus fv minus bias. So we can clearly see why that's the case. Let's say I want to do 3 plus minus 3. So this would be equivalent to adding 4. Sorry. So basically we are adding 0, 1, 0, 0 plus 1, 0, 1, 0. So this is 0, 1, 1, 1. So this in decimal is 14. Then we need to subtract the bias, which is equivalent to 7. So if we subtract this in decimal, we get 7. And what is 7? 7, well, is the representation for 0, because in our system, f of 0, the representation of 0 is 0 plus the bias, which is 0 plus 7 equal to 7. So what do we have? We have f of 3 plus minus 3 is equal to f of 0, which is exactly the answer that we wanted. So the advantage of this system is that there is only one representation for 0, which is the bias, and 0 for 0, two representations are not there. The other is that doing addition and subtraction is fairly easy. There is absolutely no problem in doing an addition. Subtraction can be slightly difficult, not very difficult though. So if you consider subtraction, so let's try to subtract f of 3 minus 3. So this is essentially equal to so in this case, instead of subtracting the bias, you add the bias. So this is equal to 7, which is the same as. So subtraction is also easy, but multiplication is difficult. So now we have seen three kinds of systems. One was the ones complement system. One is this particular approach, which is the bias based approach, and other was the sign magnitude system. So let's now discuss one approach which is used, and it is used for a very good reason, that it has very good. So what are the reasons once again? The reasons are we need one representation for 0. That is point number 1. We should have some nice mathematical properties in the sense that we should be able to nicely add and subtract and multiply the numbers, maybe not divide. So all our previous representations were simple, but they fell short. So let's do one thing. Let's consider the set of all 4-bit numbers and try to represent them as a circle. So this is called a number circle. So let's just consider 0, 1, 2, 3, 4, 5, 6 till 15, and from 0 till 15. So each one of them I have its binary unsigned representation. And so one thing that you see is that at 15 and 0 I have placed a line like this as a discontinuity. And as I travel clockwise, the numbers are getting incremented. So clockwise I increment, and if I travel anti-clockwise, which is the other direction this way, I am decrementing the numbers or reducing the numbers by 1. So what I can do is I can do something really interesting. I can take the same number circle and use the concept of the sign bit. So I can treat all of these numbers from 0 till 7 as positive numbers, and after 7, uh, I can treat them as negative numbers, but I'll treat them in a negative number in a special way. So after 0, 1, 1, 1, the next number is 1, 0, 0. So let me call this minus 8, and then minus 7, minus 6, minus 1, and so on. So the red ones over here are my set of negative numbers. So note that in this case, the point of there is no discontinuity at this point. So you have minus 1 here and 0 here, but there is a point of discontinuity over here that we call the breakpoint. So let's now take a look at some of the salient features of making a number circle like this. As I move clockwise, I essentially increment the number other than at the breakpoint. So as you see, as I move clockwise, I'm incrementing the number. So this is feature number 1, that this clockwise increment is there in this particular number circle. Second, the notion of the sign bit is there in the sense that if you take a look at all the positive numbers, their MSB or the most significant bit is 0. And if you take a look at all the negative numbers, their MSB or the most significant bit is equal to 1. So in that sense, the notion of the sign bit is there and it has been preserved. So this will come useful. So let's now try to use the number circle. So let's assume that you want to add m to a number n. So the first thing that we do is we locate n on the number circle. If m is positive, we move m steps clockwise, because every single step that we move, we increment the number by 1. Similarly, if m is negative, we move m steps anti-clockwise. Or so moving m steps anti-clockwise will essentially decrement the number, and this is equivalent. So here is a very important point. So in this case, let me consider this point 4. I want to subtract 2, so I can move 2 steps anti-clockwise. One step, second step. So moving 2 steps anti-clockwise is exactly the same as moving 14 steps clockwise. Right? So this is a very important point that all of us need to remember. This is the crux of this approach, that moving 2 steps anti-clockwise is exactly the same as moving 14 steps clockwise, which is exactly what we are trying to say, that in an n-bit number system, moving m steps anti-clockwise is the same as moving 2 to the power n minus m steps clockwise. Clearly, if we cross the breakpoint, we can have an overflow, which means that the number is too large or too small to be represented, but we'll discuss such special cases later. So keeping these things in mind, let us define the 2's complement notion. So the 2's complement notion is something like this. So we'll represent positive numbers as we were doing, as long as a number is between 0 and 2 to the power n minus 1 minus 1. So in a 4-bit number system, 2 to the power n minus 1 is 2 to the power 4 minus 1 and minus 1. So this comes out to be 2 to the power 3, 8 minus 1, which is 7. So as long as a number is between 0 and 7, all inclusive, we will represent it as u, which is exactly what we are doing in the number circle. That a number between 0 and 7, let's represent it as the unsigned binary representation of the number itself. However, if a number, the moment it becomes negative, then what we will do, and the number is between minus 2 to the power n minus 1, which is like in a 4-bit number system minus 8 and 0, we will represent this as 2 to the power n minus the absolute value of u. So this is very interesting why this is done. So let's start from point 0. Let's assume that I want to represent minus 5. So minus 5 is the same as 0 minus 5. So I should walk 5 steps anticlockwise. So 1, 2, 3, 4 and 5 I reach over here. So as I said, the crux of the idea is walking 5 steps anticlockwise is also walking 11 steps clockwise. So the representation of minus 5 should be the same as walking 11 steps clockwise, which is plus 11. And you would see this is exactly the case, that we have 8 plus 2 plus 1, which is plus 11. So this is exactly what is being shown in this formula over here, that in the number circle, representing a number of the form u where u is negative is the same as 2 to the power n minus the absolute value of u. So this is like walking u steps, absolute value of u steps anti-clockwise from 0, or moving these many steps clockwise. So fu in this case is the index of a point on the number circle, and this will vary from 0 to 2 to the power n minus 1. So simple examples for plus 4, what do we do? For plus 4, what we do is we represent it, it's within the range of the number system 0 and 7. So we represent this as 0, 1, 0, 0. For minus 4, the way we represent this is very simple. We just do 16 minus 4, which is 12. And this is exactly the representation of 12 in the binary system, which is 8 plus 4 is 12. Similarly, for plus 5, what we do is that we represent this as a regular unsigned binary integer, which is 0, 1, 0, 1. And for minus 3, well, it's very simple. We just to take a look at the formula over here, and its representation will be 16 minus absolute value of 3, which is plus 13. And this is plus 13 is 8 plus 4 plus 1, which is 12 plus 1 equals 13. Now let's consider properties of the 2's complement notation. So typically in any notation, the first property that we look at is the range of the number system. So what we had seen is that for a 4-bit number system, the range was between minus 8 to plus 7. This can be extended to an n-bit number system, where the range is between minus 2 to the power n minus 1. So you can substitute the value of 4 over here and you'll find it's minus 8 to plus 7. So this is the first property. So one thing that we can infer from here is that we have one more negative integer than the number of positive integers. But that is because we have to accommodate for 0 also. There is a single unique representation for 0, which is all zeros, which is a very good thing. This is something that we wanted. The most significant, so the third property is that the most significant bit of fu, which is the representation of a signed number in this notation, is equal to the sign bit of u. So why is this the case? Let's go back to the number circle, and the answer is there. So if we consider all the positive numbers, their most significant bit is 0, which is the sign bit of the number. If we consider all the negative numbers written in red, their most significant bit or sign bit is plus 1, which is what we get to see for all the numbers over here. So it's very easy to find if a number in the 2's complement notation is positive or negative. We just take a look at its MSB, the most significant bit. So alternatively, this is more of a generic proof that if fu is less than 2 to the power plus n minus 1, the MSB is 0, you can infer it's positive. And for a negative number, it needs to be greater than or equal to 2 to the power n minus 1. It needs to cross the breakpoint in the number circle. This is the breakpoint. And at this point, the MSB becomes equal to 1. Thus, the number is negative. Now let's look at some more properties. So every number in the range of the number system has a unique mapping because it has a unique point in the number circle. So why is this called the two's complement system? We'll take a look at it in the next two properties. But first, let us define something simple. We define this point, this operator called equivalence with three arrows. I'm sorry, three horizontal lines. This means that they refer to the same point on the number circle, or alternatively, A is equal to B mod 2 to the power n. And so we can see why. So let's consider a 4-bit number system. And so let's consider point 3. If we add 16 to 3, then we just need to walk 16 steps in the clockwise direction. We'll again come back to 3. So essentially 3 is equivalent to 19 in this system. The reason being that 3 is equal to 19 mod 16, where 16 is 2 to the power 4. So the advantage of having this particular notation is that we can say that a lot of numbers on the number line are equivalent because there is only one representation for them on the number circle, and out of them only one is in the range of the number system and the others are not. So now let's come to the first serious property of the two's complement notation. So let's take a number u. So we want to find the notation of the number minus u. So this is equivalent to, where this is the same operator that we have defined, 2 to the power n minus f of u. So this is, so let me first give an example and then we will look at the proof of this. So consider the representation of minus 4. This is equal to 16 minus the representation of plus 4. The representation of plus 4 is just 4. So this is essentially equal to 12's binary representation, which is 1100. So it is very easy to find the representation of the negative of any number simply by subtracting it from 2 to the power n. And this is also why this is called a 2's complement number system, because we are subtracting it from 2 to the power n. That's the reason. Now, if we want to take a look at a proof of this, this can easily be proven again with the number circle method. So this is how we'll define a number circle with a breakpoint over here. So what we want to do is that if you want to find f of minus u, this is same as moving a few steps counterclockwise. Is this, so basically moving a few steps in a counterclockwise direction is the same as moving 2 to the power minus a few steps in a clockwise direction starting from 0. So what we are saying is that assume, let's consider if u is positive, then we'll have f of minus u is 2 to the power n minus u. So what we need to do is that the location for u in the number circle is, let's say, this point, and the location of minus u is, let's say, this point. So f of minus u we can get by essentially starting at 0 and walking 2 to the power n minus u steps in a clockwise direction, which will bring us exactly over here. Because if you walk 2 to the power n steps, we'll again come back at the origin, and at this point we'll exactly reach 2 to the power n minus u, which is exactly the same as walking minus u steps in the counterclockwise direction. So what we can see is that if u is positive, this relationship holds. Similarly, if u is negative, it's also easy to prove this same relationship. This I leave for the reader. But the important point to note in this number circle based logic is that walking u steps in a certain direction is same as walking 2 to the power n minus u steps in the opposite direction. This is a very important point to understand for all of us, that in a number circle, when you're walking in one direction, you're incrementing, walking in the other direction, you're decrementing. So when we, let's say, want to compute the notation of minus u, f of minus u, so minus u basically means that we start at the origin and we move u steps in the counterclockwise direction, which is exactly the same as we move fu steps in the clockwise, uh, I'm sorry, which essentially means that we move 2 to the power n minus fu steps in the clockwise direction to reach the same point. So now let's take a look at some of the basic properties of a 2's complement number system and see how, what's the real advantage of this. So actually the 2's complement system has some wonderful properties, mathematical properties, and that's very interesting. So let's do one thing. Let's start at a point u. So what we want to prove is a basic rule for addition, that f of u plus v, where we are adding two numbers, their representation on the number circle, the point, is the same as fu plus fv. So this basically means that we can add the representations of u and v. We can just do a simple binary addition, and that will be the representation of u plus v. So what do? We start at point u. Its index is fu. So let's first assume that v is positive. So then we move v points clockwise and we'll arrive at fu plus v. So its index will be equal to fu plus v mod 2 to the power n, and since v is equal to fv, we will have this relationship, which is exactly equal to this relationship, is just equal to represented by, substituted by the equivalent sign. So we will thus have for positive v, f of u plus v is exactly the same as fu plus f of v. So let me give an example to explain this point. Let's assume we want to add 2 plus 3 in binary. So the representation of this would be 0010 plus 0011. Right? So basically we can say that f of 5, which is 2 plus 3, is equal to f2 plus f3, which is equal to 0010 in binary plus 0011, which is 0101. Now let's consider v to be negative. So if we consider v to be negative, what do we need to do? We need to start at the point u on the number circle with representation fu, and we need to move modulus of v points anti-clockwise. So this is the same as moving 2 to the power n minus mod v points clockwise. So we will then arrive at fu plus v. Since fv is equal to 2 to the power n minus mod v, the index fu plus v, this number will be equal to fu plus 2 to the power n minus mod v, mod 2 to the power n of course, which is equivalent to fu plus fv mod 2 to the power n. So what we see is that this relationship holds for both positive v as well as negative v. So let's consider again an example. Let's assume that we want to compute 2 plus minus 4 in binary. So the representation of 2 plus minus 4, what we are saying is f of 2 plus f of minus 4. So f of 2, if we consider in binary, 0010. If I consider f of minus 4, that is essentially equal to f of 12, 16 minus 4, which is 0010 plus 1100. So let's proceed and add, no problem. So what we get is we get 1, 1, 1, 0, which is actually the representation of, so this is plus 14 because this is 4, I'm sorry, 2 plus 4 plus 8, which is plus 14, which is actually f of minus 2, which is exactly the answer that we needed to get. 2 plus minus 4 is minus 2. So what we can see is that both for positive v as well as negative v, if we need to add two numbers where they're represented in their 2's complement binary notation, we just simply need to add them, and the final result will be the representation of what the final result should be. Right? The result of this addition over here will be the representation of what the final result, which is u plus v, should be. Now let's consider subtraction. Let's assume we want to subtract u minus v. So this from the previous theorem is fu plus f of minus v, which is fu plus 2 to the power n minus f of v. So subtraction in a sense is the same as addition. You just compute the 2's complement of fv. So let's consider an example. Let's say that I want to subtract in a 4-bit number system 3 minus 5. So this I can write as f of 3 plus 2 to the power n, which is 16, minus f of 5. So we'll be writing in both binary and decimal notations. The notation needs to be sort of inferred from the context. So in this case, f of 3 is equal to 3. So I'm not writing it in binary to just keep the representation simple. And f of 5 is equal to 5. So this is equal to 14, which is equal to f of minus 2. This is exactly what we wanted to prove. So one thing that we see is that adding or multiplying, adding or subtracting 2's complement numbers is actually very easy. For addition, we just go ahead and add, and if we want to subtract, we essentially add it with its 2's complement. So here is a trick question, food for thought. Does a similar relationship hold for multiplication as well? Right? This is something that needs to be proven, and this actually does hold. So this actually does hold, and this is a very nice property of the 2's complement notation. It doesn't hold for division, but at least for multiplication, this property definitely does hold. And this is a very, very useful property. So let's maybe consider an example. So let's consider you want to multiply 2 times minus 3. We claim that this is equivalent to f of 2 times f of minus 3. So f of 2 is equal to 2 because the representation of 2 is 2 on the number circle. And similarly, f of minus 3 is actually 13 because it's 16 minus 3. So this is equivalent to 26, which is equivalent to 10 because we take always mod 16. So mod 16 means consider the 4 lower bits. And so this is equivalent to 10, or I can write 26 mod 16, which is essentially equal to 10, which is equal to f of minus 6. Why minus 6? Because f of minus 6 is equal to 16 minus 6 is equal to 10. So this is exactly what we had set out to prove, that f of 2 times minus 3 is f of minus 6. And lo and behold, we have a proof over here. So now the question is that we want to prove this result for any arbitrary u and v. So let me prove some of the subcases, and some cases I will leave as an exercise to the reader. Consider u and v both are positive. If both are positive, then we have f of u times v is just u times v. Of course, when there are no overflows, we'll discuss that later, multiplied by u times v, which is trivially true. Consider the fact that both u and v are negative. So then let's look at, so if u and v both are negative, the product is positive. So the RHS is still u multiplied with v, whereas the LHS is 2 to the power n. So maybe I can just write it mod u times mod v just to make things straightforward. So since we take all of these numbers mod 2 to the power n, so why do we do that? Because the range of the number system is n bits. More than that we can't represent. So since we take everything mod 2 to the power n, we can cancel out all of these terms. So since this term gets cancelled and this term gets cancelled, what we are left with is mod u multiplied with mod v, and thus LHS is equal to RHS. The only other case that we need to prove is when u is positive and v is negative, and when u is negative and v is positive is an exactly symmetric case, so we just need to prove one. So the reader needs to prove the case when u is positive and v is negative. The reader needs to prove this result, and this I leave as an exercise. So how do I compute the 2's complement very quickly? Well, let's take a look at what needs to be done. Uh, so one thing that can be done is that, let's say I want to compute the 2's complement of 4, minus 4. So in this case, what do I do? What I do is that I do 16 minus 4, which is 12. So I am essentially subtracting 4 from 2 to the power n to get 12. So I am doing a computation of the form 2 to the power n minus u, which can be broken down into 2 to the power minus n minus 1 minus u plus 1. If readers would kindly recall, this is the 1's complement. So 2 to the power n minus 1, let's see what kind of a number it is. For example, consider 2 to the power 4 minus 1, which is 15. It's 1, 1, 1, 1. So 2 to the power n minus 1 is essentially equal to 1, 1, 1, 1 n times. Say this minus any binary number at every point would just assume you have a 1 over here, you'll get a 0 here. You have 0 over here, you'll get a 1 here. So you just get the complement of the number. So this is called the 1's complement. So what we can do is that we can take the 1's complement and add 1 to it, which is exactly what we get to see in this particular representation. This is a nice way in binary to actually get the 1's complement of a number and to add 1 to it. So for example, if we want to compute minus 4, we first find the complement and then add 1 to it, and this is the representation of minus 4. Now let's take a look at one more trick in the realm of 2's complement numbers. It's called sign extension. So suppose we convert a n-bit number to a m-bit 2's complement number, right? So the idea here is that assume that this is a 4-bit number and you want to convert it to an 8-bit number. So what do? So assume that the number is positive. So in almost all proofs, we sort of divide it into two subcases. In one subcase, the number is positive, and in the other subcase, the number is negative. So let's consider that I have a number of the form in a plus 4 represented in binary 0100, and I want to convert it into an 8-bit positive number. All that I need to do is that in the 4 MSB positions, most significant positions, I add 4 zeros. So this is a valid representation in a 8-bit number system. Now let's assume that the number is negative. So let's consider minus 4. So minus 4's representation is 1100 in the 2's complement system. So we need to calculate what would be the representation of minus 4 in a 8-bit number system, right? So minus 4, how do we get this number? This is actually the decimal form is 12 and this is 16 minus 4. In 8 bits, we need to compute 2 to the power 8 minus 4. So 2 to the power 8 is 256 minus 4. So let's do a little bit of algebra. So let's assume, so this is the representation of number in the m-bit number system. This is the representation of the number in the n-bit number system. So let's just subtract. If we subtract, we get 2 to the power m minus 2 to the power n. So if we would actually subtract it, what we would find is the result is 2 to the power n plus 2 to the power n plus 1 till 2 to the power m minus 1. So maybe just giving an example, let's say you want to subtract 2 to the power 4 minus 2 to the power 2, which is 16 minus 4, which is 12, right? So the claim here is that this is equal to 2 to the power 2 plus 2 to the power 3, which is 4 plus 8. So this is a very easy identity to prove, and so I leave this to the reader. But the interesting part is that if I take this expression and I convert it into binary, what I would get is that I would get n zeros and the remaining m minus n ones. Alright? So this is exactly what I would get, that I would get n zeros and m minus n ones. Now assume that the representation in a 4-bit number system of a number of the form minus u, right, where u is positive, is 2 to the power n minus u. And let's say in an 8-bit number system, we have this equal to 2 to the power m minus u, where n is 4 and m is equal to 8. So what we have this relationship over here, that f of 8 minus u is actually equal to 2 to the power n minus u, which is again an n-bit number, right, which is an n-bit number, plus this expression over here, where the first n bits are all zeros and the remaining ones are all ones. So I would consider a relationship of a number of this type, which has m minus n ones and the rest n are zeros, right? So if I add this number plus this number, what I will get is that the first m minus n positions, will still be, the first m minus n positions will still be ones, and then the remaining positions over here will be occupied by whatever is the representation of 2 to the power n minus u, right, for the remaining n positions. Since this number is negative, the MSB of this part will also be 1 and the remaining will be ones. Alright? So the important point to note is that whatever is the representation in the 4-bit number system, so let's again consider f of minus 4. F of minus 4 in a 4-bit number system was 1100. So f of minus 4 in an 8-bit number system will first be 1100 and the rest, all the positions will be equal to 1. So the readers can manually verify that this is exactly what comes via another calculation, which is 256 minus 4. So this is also the representation of 252. Alright? And so what we see is that the sign bit over here, we can think of it as getting replicated across the rest of the new positions. This is exactly what was happening for positive numbers, that the sign bit for the 4-bit number was getting replicated across the new positions, that new positions to the left, and here also the sign bit is being replicated towards the new positions on the left. So this trick is called sign extension, that to convert a negative number from a n-bit number system to an m-bit number system, you add m minus n ones in the most significant MSB positions. So what we can do, just summarizing and closing the discussion, is that in both cases extend the sign bit by m minus n positions. For example, if I want to convert from a 4-bit to an 8-bit system, uh, number system, and my number is 0010, all that I do is I add 4 zeros to the left of it. If I have one number of the form 1011, I just add 4 ones to the left of it. So essentially, I take a look at the sign bit. Whatever it is, I just extend the sign bit or replicate it across the positions to the left. Now let's consider one more point, which is called an overflow theorem. So the overflow theorem is something like this. So let's assume that in a 4-bit number system, we want to add 5 plus 5. So 5 plus 5, the answer is 10. But 10 cannot be represented in 4 bits. The reason being that the largest number that can be represented is actually plus 7. So in this case, we say that we have an overflow, which means that the number cannot be represented in the particular number system. Similarly, if I add minus 5 and minus 5, it will be minus 10. But the range of the 4-bit number system is only till minus 8. So we can't do the addition. As a result, we'll also have an overflow in this case. So the overflow theorem is something like this, that if I'm adding u plus v, and if uv is less than 0, which means one of the numbers u or v is positive and the other one is negative, we will never have an overflow. So to prove this, let us go back to the number circle. So there will be an overflow only when we cross the breakpoint. Otherwise, we are within the range of the number circle. So if uv is equal to 0, one of the numbers is, if uv is equal to 0 means one of the numbers is 0. So if one of the numbers is 0, there will not be any overflow. If uv is greater than 0, an overflow is possible. And we just saw an example of this where we are adding 5 and 5, or adding minus 5 and minus 5. Now uv is less than 0. Let's see what will happen. Let's say that we want to add 1 and minus 4. So we start at 1 and we count 4 positions in the anti-clockwise direction. So we can clearly see that we are not crossing the breakpoint, so there is no overflow, right? This is the breakpoint. But if we had u and v both as positive, and in this simple 2-bit number system that we have, we can clearly see that we are crossing the breakpoint and there will be an overflow. So I'm adding 1 and 3. So to add 3, I need to move 3 steps clockwise and I will cross the breakpoint. And so 1 and 3 is not minus 4, it's actually plus 4, is the wrong answer. So I'm having an overflow. So what are the conditions for an overflow? If uv is less than equal to 0, we'll never have an overflow. If uv is greater than 0, means they have the same sign, we can have an overflow, but when will we have? We'll have an overflow when the sign of the result is different from the sign of both u and v. Right? In this case, u and v both are positive, and we add them. If the result is negative, we know there is an overflow. Similarly, if let's say we are adding minus 3 and minus 2. So I can start at minus 3. To add minus 2, I need to travel 2 steps in the anti-clockwise direction. So I come here and then I come here, right? And so the answer that I get is plus 3, which can never be the answer because minus 3 and minus 2 are both negative numbers. So the answer cannot be positive. So then also I'll find that I am having an overflow. So in the book, there is a very detailed proof of this result. And so in the slides, this is our last slide, so we are not presenting a result. But I'll just give you an overview of the proof. But the detailed proof is there in the book, and I would request all readers to go to the book and take a look at the proof. So the proof goes somewhat like this. So let's go back to this example. So let's assume that, with no loss of generality, u is positive and v is negative, right? uv is less than 0. So if I start at a positive point, to have an overflow, I need to sort of cross this breakpoint, right? So to cross this breakpoint, so let me assume by contrapositive that you can have an overflow. So the best possible way that I can have one, to maximize my chances, I would like to make u as small as possible and the absolute value of v as large as possible. So the smallest value of u that is not negative is 0. And the largest absolute value of v is actually 4. So the v will become minus 4. So if I add 0 plus minus 4, I will still come over here, which is in the range of the number system, and I will not cross the breakpoint. Right? So basically, whatever I do, I will not be able to cross the breakpoint, and thus I'll not have an overflow. So this is a very high level hand wavy kind of proof, but a better proof and a very rigorous mathematical proof is there in the book. That's the reason I'm asking you to go there. And similarly, if I consider any other example, let's say I start at 2, I need to travel more than 7 steps to actually cross the breakpoint and sort of need to add minus 7. And since minus 7 is not in the range of the number system, we'll not have an overflow. So this is why if one of the numbers is positive and the other is negative, or the other is 0, we will not have an overflow. But if both the numbers have the same sign, we can always cross the breakpoint, as we have seen. Now a reader can argue that is it possible for the two numbers to have the same sign, and I will cross the breakpoint, have an overflow, but the result will also have the same sign, which means maybe I start from this point, I add a positive number and I walk all the way up, and then again my result is in the positive half of the number circle. This will never happen. The reason this will never happen is, so my best case is that I start at, let's say, 3 and add 3. So one step, 2 and 3, so the result is still negative. And in the other case, I can start at minus 4 and add minus 4. In this case, one step, two step, 3 and 4, right, because I'm walking anti-clockwise now, the result is still non-negative. So what we see is that irrespective of whatever you do, if I'm adding two numbers with the same sign and the result is of a different sign, of the opposite sign, I can always infer an overflow, which is exactly what the overflow theorem is trying to tell you. That if one of the numbers is 0, we'll never have an overflow. If one is positive, the other is negative, we'll never have an overflow. Only when both the numbers u and v have the same sign would we actually have an overflow, and the condition is that the sign of the result should be different from the sign of both the numbers.